Well, it's a pleasure and an honor to be able to contribute here. I will. I think I'll give you a very simple talk, which at the end of the day may be just as well. At the end of your day. Oh. I will do some statistical mechanics in the hyperbolic plane. I guess we all know the hyperbolic plane is just a 2D manifold with a uniform negative curvature. The plane with a uniform positive curvature is the sphere. And we all know, I think, that the sphere can be mapped conformally to the complex plane. By this formula. W is the position in the complex plane, and theta and phi are just the angles, the regular angles in the sphere. And in the same way, the hyperbolic plane can be mapped onto the plane by just replacing the tangent by the hyperbolic tangent. I'm trying to but then since the hyperbolic tangent is bounded between the plane is mapped onto a disk rather than the hyperplane is mapped onto a disk rather than the whole complex plane. Now just to see the mapping, analogously to that for the sphere, you may have seen this picture if you have the sphere and we just have a metric, ordinary Cartesian metric in three-dimensional space. We can map the position on the sphere onto the plane by drawing the line from say the South Pole all the way to through the point until it hits the plane. So this point is mapped there. This point is mapped here, and that happens to be a conformal map. The map for the hyperbolic plane looks very similar. We take the central point on one side of the hyperbole, and we connect that point to a point on the hyperbola, and the point where it crosses the plane will be the projected point. But now the metric is also hyperbolic, so we have dx squared plus dy squared, which is the horizontal here in this direction, minus dz squared, the vertical. And so this maps the hyperbolic plane onto the disk. Now, the area of a disk, of say a finite disk in the hyperbolic plane, increases with the radius by this formula, just 2 pi times hyperbolic cosine minus 1, and this grows eventually much faster than that of the ordinary plane. So if you think of, say, a random walk, then the random walk has many more ways to escape than in the Euclidean plane. If you think of a discrete random walk with discrete steps, it could be on a lattice or in the continuum, but the steps are discrete, and I give a weight to the probability to take the next step. So the probability is between taking another step or terminate the walk. If that weight is small, then the random walk will be finite. If that weight passes a critical point, the random walk will be infinite. And that phase transition we have in the plane and just as well in the hyperplane. But there is a big difference. In the plane, once the walk is infinite, it will also be space filling. It will cover a finite region of the lattice, while in the hyperplane, this may not be the case. And we'll come back to similar deviations in other models. Now, let me come to the original work that motivated me to do this. It is work by Tobias Müller. He did percolation in the hyperbolic plane. And just to remind you, and he did it in the continuum. So I will remind you of how this can be done in the Euclidean plane. We just use a uniform Poisson process, sprinkling disks in the plane with some density. And disks that overlap, we consider connected. And if the density is small, then the clusters will all be finite. But when the density passes a critical point, an infinite cluster will form, and it will cover more and more of the space. And once there is an infinite cluster, there is only one. And that is a property that we will come back to. And I'm a little bit bothered by the screen that shows me. Or maybe I can. Yeah, now it's gone. When we can look at the size of the largest cluster, the number of disks it contains, and then when the density is less than the critical density, the size will remain finite. So n as a function of the area of the disk in which I play it is just of order 1. At the critical point, the size grows with the area as a power of the area, given by 43 over 48. And when the density is larger than PC, then the largest cluster is of the same order as the area, because it covers a finite fraction of the area. Now, in the hyperbolic plane, this will be different. Of course, we can also do percolation on the lattice, and we all know that you can do bond percolation, side percolation, but that is not much of an relevance here. But What is important is that the exponent 43 over 48 is the same in the continuum and in the lattice, irrespective of the kind of lattice and irrespective of the size or shape of the particles. And that property, of course, we know as universality, and that plays a major role in my talk. Now, we look at percolation in the hyperbolic plane. And it has been observed that this has two transitions. For small p, there is no infinite cluster. For intermediate density, there are infinitely many infinite clusters. And for high density, there is one infinite cluster. And this, then we can again look at how the central cluster or the largest cluster increases with the size of the disk where the finite disk where we play our model. And Tobias Müller studied this, and he proved that for all density, the size of the largest cluster increases as a power of the disk, the area of the disk for large areas. And that power is 0 when at small density, and it is 1 at high density. And in the intermediate density, it increases continuously from 0 to 1. And this he actually proved. And I was quite intrigued by this result, and this attracted me to the subject. It reminded me of the excitement I felt and my collaborators felt in the early 1970s when we learned of Baxter's solutions of the 8 vertex model. We had just gotten used to the idea of universality and saying that critical exponents do not depend on the details of the interaction. And now we had a counterexample. And this created some panic in the community, and it motivated a search how to save the concept of universality. And eventually, universality was saved, but restricted. It was formulated by a number of people. First, that varying exponents are exceptional. And in these exceptional cases, all critical exponents depend on only one parameter. And before I continue, let me say a few words of why we should believe or expect universality. The first is we just observe it. And the second is it is predicted by the theory of renormalization. In renormalization, you see similarities between models on as you rescale the system, and as you rescale the system, you follow in the parameter space, the coupling constants, you follow the arrows, and if the fat line is the critical surface, and on the fat line you approach a fixed point, and all the critical properties are effectively derived from that fixed point. That follows from the concept of renormalization, if it is true. Now, why would we believe in renormalization? Again, we observe it. Now, in the hyperbolic plane, you might view renormalization as problematic because there is an intrinsic scale, the radius of curvature. And in the model, you can think I have three scales that are defining the system. The microscopic scale, say the size of the particles, if you, or the lattice constant of the lattice. And then there's the radius of curvature, which is intrinsic in space. And there is the radius of the domain. And when indeed the radius, the microscopic radius is much smaller than the radius of the domain, you would think a field theory as a continuum limit is natural. At criticality, you would expect a conformal field theory. And we will actually work in the limit that the radius of the particles, or the microscopic radius, is of the same order as the radius of the curvature. This permits us to use regular lattices, to which I'll come very soon. And of course, these two scales are much less than the size of the radius. But before we used a lattice, we first redid what Tobias Müller did. And we thought, could we perhaps estimate this exponent psi as a function of p? And indeed we can, but it's just a relatively boring function. And of course, it will depend on the details of the model. If I take say, a different radius of the disk, or I can take different shapes of the particle, this function will not be universal. But if we have two exponents and both depend on only a single parameter, that would imply that if I take the one exponent as a function of the density and the other exponent a function of the same density, then I can eliminate this density and find the second exponent as a function of the first. And this function could be universal. So we thought of exponents to study besides the size of the largest cluster. Well, a natural exponent that we know from 2 dimension is the perimeter length of the central cluster. This the perimeter of separating the largest cluster or the central cluster from its surrounding. But unfortunately, this this exponent is always 1 in the even in the intermediate phase. And actually, it's not so surprising because the circumference of even a compact disk increases exponentially with the radius. So a curvy linear, I mean, something as complicated as the perimeter must also at least increase, must also increase at least as fast as the perimeter of a disk. And the disk already has a perimeter that has an exponent 1. And the second attempt we took is the radius of gyration of the largest cluster, but that also ran into difficulty. We found again an exponent which does not depend on parameter. But finally, we were saved by the idea of the size of the dual cluster. If you have percolation, you can think of the clusters, but you can also think of the space that they leave uncovered. And that, again, is the percolation process. And that the clusters of that empty space are also for the empty space also forms clusters, and I can look at the largest cluster of those. And so when the exponent psi increases from 0 to 1, then the exponent of the dual cluster must decrease from 1 to 0. And you might expect the sum to be 1, but it is some function, and we would want to know if that function is universal. It is not difficult to define this in the continuum, but it is very difficult to measure. So this was a reason to turn to lattices. And just a few words about lattices in the hyperbolic plane. I take a regular lattice to have vertices, edges, and faces. And I want all the vertices to be equivalent, same with the faces. And I can define then the lattice by saying how many edges go around the face and how many edges touch at a single vertex. So I have two numbers, f and v, and the number f, the number of edges at a face, and v, the number of edges at the vertex. And the pairs 4, 4, 3, 6, and 6, 3 we know as the square and the triangular and the hexagonal lattice. And the pairs 3, 3, 3, 4, etc. are the Platonic solids. But if the numbers are bigger than these pairs, then you form lattices like these. Say 3, 7, 7, 3, 4, 5, 5, 4. And in these lattices, there is, again, a dual, like in lattices in the Euclidean plane. Say here I have black, the 3, 7 lattice, and red, the 7, 3 lattice, and they are each other's dual. Now, so we used these lattices and measured the exponent. Now, if psi is the exponent relating the size of the central cluster to the area of the disk, sorry for the misspelling, and the corresponding exponent psi d for the dual cluster. And these are the graphs that we find of one exponent versus the other. And so indeed, you see that for these lattices, they look at least similar. The statistics are not very good, but the statistics are okay to at least plausibly believe that this exponent is indeed, these exponents are indeed universal. The relation between these exponents are universal. Now, to improve our data, we started to use another method, which I will share, and that is makes use of the corner transfer matrix. Another famous invention of Baxter, at least Baxter made the corner transfer matrix famous. If you have a corner transfer matrix for a, say, small finite space, you can make it bigger by adding by multiplying it by a linear transfer matrix of this, say, this bar, and then now it is no longer isotropic. It's horizontally, it's smaller than vertically. So I add also the longer beam at the vertical direction, and then I have a bigger corner transfer matrix. And I can use a similar trick for this linear transfer matrix. I add a little square in order to make it bigger. And this is something we can, so you can use this to calculate exactly the corner transfer matrices of small lattices. And you can go beyond small if you make an approximation by projecting while you do the multiplication, you project on the eigenspaces of the largest eigenvectors of the corner transfer matrix. And this is known as the corner transfer matrix renormalization group, the CTMRG. And this can be generalized to the hyperbolic lattice. Say, we can use the first figure as I could view this as a wedge. I consider the fat edges as edges which I will merge into other parts of operators. And then so this is a wedge, and I call this a beam. This has 3 edges which will be used to merge, and I can turn them into a bigger size. First, I will color them differently to just see the difference well, and then I increase the size by appending them on a central hexagon or a pentagon. So I have 3 beams and 2 wedges to make a bigger wedge. And I have 2 beams and a single wedge to make a bigger beam. And this I can continue, in fact, ad infinitum. First, I will just color the bigger wedge and the bigger beam uniformly. And the next picture is already a large system. I can continue this as far as possible. And this, in principle, allows me to calculate partition sums and exponents. Unfortunately, I haven't achieved actual results yet, but I found the method interesting enough to share. And I would like to conclude with the remark that Baxter has always inspired me throughout my career since I learned about this 8 vertex model. Thank you very much for your attention.
Any questions? Any questions, Bernard?
One on the chat, that was me, actually, something else.
Somebody else?
No, that was me.
Okay.
Oh,
So I have a question. So what's the conclusion? Do you have universality on the hyperbolic way or not?
Well, so far my conclusion is yes, but I would like to base it onto a firmer basis, which unfortunately will remain numerical. I don't think that anything can be done exactly, even though a lattice like the well, say the lattices look very much like this in particular, like a lattice that was studied by Baxter in his paper in the Proceedings of the Royal Society. I don't remember the year, but a lattice made up out of arbitrary lines, a planar in the plane. And these lines are indeed form a planar combination of lines, but I find no way to use spectral parameters such that the interaction is uniform, is the same at every vertex.
But if the Coulomb transfer matrix on the plane works very well if you calculate the partition function or the order parameter, it's extremely numerically extremely accurate because the method is formulated for infinite lattice, and if everything is done correctly, you out of critical point it converges very fast, but in critical point it doesn't converge.
Yeah, of course we have to apply it in the critical regime to, but this is what I'm attempting. But so even the simulations give some confidence that the exponent is universal, even though renormalization is problematic.
Okay, let's take this thing again.